Our heat transfer project was to measure the temperature of an oil-filled radiator and model where and how much heat transfer was coming from it, and then find a design that may be safer for use in the home while producing the same heat transfer. The idea for this project stemmed from my niece that constantly wants to crawl over and touch the heater where she has access to some of the hottest portions of it. From my experience with it, we know it is too hot for her to touch as parts of it will start to burn my fingers after less than a second touching it, thus making it truly unsafe for anyone, especially children. Through research, the closest recommendation we found was a recommendation that water heaters are set at or below 120 degrees Fahrenheit to avoid scalding burns for young children. Even though this value is for a home water heater, we feel that this value would be an accurate representation of what temperature a hot household item can be at to avoid very serious burns. Thus, this value would be used as our benchmark for the desired temperature of the heater when we did our optimization.
We measured temperatures at multiple points along both cylinders of the radiator as well as along the centers and edges of each fin. In addition, we measured the temperature at multiple points on the front area of the radiator. These measurements were taken using a thermistor wired into an Arduino with a simple voltage divider circuit. MATLAB was used to read in the analog voltages and then convert the voltages into temperatures in both Fahrenheit and Kelvin. This allowed us to get a feel for how hot it really was, while also recording values in Kelvin for our use in our analysis.
When values were measured, we found and observed that the heating of the radiator occurred in the cylindrical portions of the heater, as well as the center of each fin. We believe this occurs because the warm oil flows through the bulged lines that span the distance between the round portions near the top and bottom of the fin in the above picture. This realization allowed us to use a one-dimensional analysis of the fins rather than a two-dimensional one that we initially thought. Our base could now be modeled as a rectangle with two fins coming from it. With this in mind, the values of each fin base were measured and the averages were recorded. The image of the back end of the radiator is an example of where the measurements were taken on the base of each fin. All these calculations were done on all 6 fins as well as on the cylindrical base portions, and an average base temperature of 267 degrees Fahrenheit was calculated. From these simplifications, it allows us to understand how to better calculate our heat transfer rate through radiation and convection of the entire system.
We were able to measure the actual power the radiator was consuming by using a wattmeter. A wattmeter plugs into an outlet and has a plug input for an appliance. This allows it to measure the amount of power being consumed and display it to a screen. The power measured by the wattmeter during our testing was 2.39 kilowatts, which is nearly 1,000 watts higher than the 1,500 watts that is reported by the manufacturer. This was unexpected to us because the radiator is barely 6 months old. Using the equations for fin arrays and radiation, we were able to approximate the heat transfer rate as 2,198 watts. The assumptions and simplifications used were considered to be appropriate because the error between the calculated and measured rates was only 8%.
To make the calculations a little simpler, the areas that were of varying diameters or had strange appearances were modeled more as plain cylinders or rectangles without any divots, bulges, or change in cross-section. An example of one of these simplifications was that of the cylindrical portion that is at the top and bottom of the radiators, which can be seen in the above image. To simplify this, we found the average diameter and used that to find our surface area. The same simplifications occurred with the rectangular fins that can also be observed in the picture above. The bulges and the divots on these fins were neglected, and the fins were modeled as plain, flat rectangular fins with a single thickness, rather than having any more complex shape. Through these simplifications, we believe that the results yielded a underestimated area that also caused us to underestimate the heat transfer?
We found that if the radiator design remained unchanged, but was limited to the OSHA maximum temperature of 115 degrees Fahrenheit, it would only output 620 watts of heat. This, being 1/3 of the heat the radiator is claimed to output, severely reduces the ability to heat a room as quickly as desired. A redesign is needed in order to maintain both safety and effectiveness. The first redesign we thought of seemed obvious at first, but proved to be entirely wrong. We figured that it would be a good design to keep the overall size of the heater the same, but simply add extra fins between each of the current ones. This would increase heat transfer and would also make the gaps in the radiator smaller, preventing anyone from reaching their hands between the fins and touching the hottest points of the heater should it reach unsafe temperatures. We thought that adding more fins would increase the heat radiated from the heater, but after running our calculations, it actually dropped the heat transfer by about 11 watts. We therefore concluded that in order to get around the same amount of heat output while remaining below the maximum safe temperature as defined by OSHA, the radiator would have to increase in size by a factor of 3. This would be a lot bulkier, but at least it would be safer. These are the conclusions that we came to after doing this project.